Hello everyone, I'm 2E, the team member of Crypto Analysis Task Force, and I'm from Nanyang Technological University. It is my pleasure to present our paper, New Techniques for Searching Differential Chairs in KECCAK. Firstly, I will give a brief description of KECCAK and introduce previous works on differential chair search. After that, I will cover our new 3-round chair cost search strategy. KECCAK permutation uses XOR and not operation in its round function. The state size is 1600 bits. It can be organized as a 5x5 array of 64-bit lengths with XYZ coordinates. Each round consists of 5 steps, including 4 linear operations, 0 pi, iota, and the nonlinear chi operation. It consists of 24 rounds. If you fix Z, you will get a slice. If you fix Y and Z, you will get a row. If you fix X and Y, you will get a lane. If you fix X and Z, you will get a column. Each step adds 2 columns to the current bit position. Row step is lane level rotation. It rotates the 64 bits of each lane by a specific offset, which is determined by the coordinates xy of the lane. The pi step is the permutation on lanes. It rearranges the 25 bits of each slice. Chi, which is the only one nonlinear component, can be treated as a row-wise 5-bit S-box. Iota step adds a round constant to the state. It adds a round-dependent constant to the first lane to destroy the symmetry. Since it has no effect on this kind of differential chair search, we just ignore it. As for the previous result on exhaustive chair search for KECCAK, in the paper Differential Propagation Analysis from the designers in 2012, they claim that 3-round chairs with propagation weight below 36 are searched completely, and the lower bound of 6-round chairs is 74. Another paper, New Techniques for Chair Search from the designers in 2017, they claim that 3-round chair costs with threshold propagation weight 45 are searched exhaustively, and the lower bound on propagation weight of 4, 5, 6-round chairs are improved accordingly. As for our result, we set the threshold to be 53 for our search strategy, but there is no theoretical proof for satisfactory lower bound, but we indeed found many new chair costs. Before I introduce our search strategy, I want to show you some definitions first. Current parity P of state F is the parity of all the columns. If P equals to 0, theta has no effect on state F, and F is called in CP kernel denoted as K. Otherwise, is out CP kernel denoted as N. We use parity and kernel to represent current parity and current parity kernel. A 3-round chair call is denoted by pair F1 and F2 or pair beta 1 and beta 2. The target 3-round chair calls means a 3-round chair call beta 1 beta 2 with propagation weight the reverse weight of F1 plus the weight of beta 1 plus the weight of beta 2 below a threshold. And here, the reverse weight of F1 refers to the optimal weight of beta 0, which can propagate to F1. As for the classification of 3-round chair call, according to whether F1 and F2 are in kernel or not, 3-round chair calls can be classified into 4 categories. KK chair calls with both F1 and F2 in kernel. NK and NN chair calls with always F1 out kernel. KN chair calls with only F2 in kernel. For the last 2 cases, the search strategies are quite similar, but for NK and NN chairs, the chair call search starts from out kernel state F1, but for KN chairs, it starts from out kernel state F2. Now, I will explain in details how the search strategy for KK chair cost works. Firstly, we need to prepare all theoretical candidate bit 1 structures for in kernel F1 with m orbitals, and then store them in a lookup table. According to the factor, beta 1 can propagate to F1, which is in kernel through the inverse of linear operation. We construct all the possible state F1. Based on the relationship between F1 and beta 1, we filter all the states F1, and then we extend forward by one round to obtain the target 3-round check. Please be noted here, orbitals refers to a group of 2 active bits in the same column. Use a concrete example to illustrate how KECCAK search algorithm works. Assume 4 orbitals at state F1 propagate to 3 slices at state beta 1 with 332 pattern. The 332 pattern here indicates the number of active bits in each slice. From the lookup table, we enumerate all possible valid slices for Z1 prime to obtain P1 double prime, P2 double prime, and P3 double prime. Through the inverse of linear operation, P1, P2, P3 are determined, and then according to the orbital relation, we can get Q1, Q2, Q3. Through the linear operation, Q3 double prime is determined. According to the valid 2-bit slices stored in lookup table, P4 double prime can also be obtained. So P4 is also fixed. After that, Q4 can be enumerated according to the orbital relation. So until now, all the 4 orbitals with 8 bits are determined. Then we filter all the state F1 by checking Q1 double prime, Q2 double prime, and Q4 double prime are all at slice Z2 prime or not, and check they result in kernel slice at state F2 or not. After that, we extend one more round to get to the target 3-round check course. Before we go through the search algorithm for cases with at least one out-kernel states, we need to know some definitions first. A group of out-kernel states F share the same parity P, so each parity stands for a subspace of F denoted by Vp. Under each parity P, there are a group of states called Parity-Bare states that can represent all other states in Vp. Other states can be generated by just adding orbitals to the Parity-Bare states, so all the kernel states in Vp can be covered by enumerating all the Parity-Bare states. Any other kernel states F can represent a set of states simply through adding orbitals to it. The subspace represented by F is denoted as Vf. The space of out-kernel states can be divided into subspaces represented by out-kernel state F. So, the parity space can be divided into subspaces represented by each parity-bare state. The search space is all the out-kernel state F. In order to cover the whole search space, we propose the ideal representative of subspace Vf. For each subspace Vf of Vp, an ideal representative state F prime is generated based on F. Generally, the ideal representative state doesn't exist in reality. It just represents the optimal number of active rows of 3-round check course of all states in Vp. It indicates the low bound of the whole subspace, so if the ideal representative of a subspace cannot meet the rate requirement T3, the whole subspace can be safely discarded. The ideal improvement assumption on out-kernel state F assumes that F1 can be optimally improved at beta 2 in terms of the number of active rows with the least number of orbitals added to F1. For Kn chairs, the ideal improvement assumption on out-kernel state F assumes that F2 can be optimally compensated with an in-kernel state F1 with the least number of orbitals added to F2. So, basically, the ideal representative of subspace Vf is obtained when F is ideally improved. The process of generating the ideal representative state of a subspace under the ideal improvement assumption and deciding whether to delete it or not is called viability check. The out-kernel state of that passes the viability check is called viable. So, searching 3-round check cost equals to generating all viable outcome states. Here is a complete process of 3-round check cost search. Firstly, we need to prepare all candidate parities. For each candidate parity, the corresponding parity-bare states are enumerated. For each parity-bare state, we conduct viability check on it and generate viable states. For all viable state up, we add one more orbital to it and conduct a viability check on the newly generated up prime. We repeat the whole process until there is no viable state anymore. For all the viable state up, we extend them forward or backward for one more round and crack the target 3-round check cost. Let's look at a concrete example to see how KN-chair search algorithm works. This algorithm starts from outcome state up to. The ideal improvement assumption states that for each active root at state up to, rather than considering only the computable bit 1, we take all the 31 patterns into consideration. It assumes all the 31 patterns are legal. For any up to with a superset of bit 1, it assumes that up to always have in-kernel state up 1. If its original active root cannot make up 1 in kernel, it can be improved to be in kernel by just adding orbitals to state up to. When adding orbitals to up to, it assumes the least number of row increase on state up to and bit 2. After that, we conduct a viability check and add one more orbital to all the viable up to. We repeat the whole process on all the viable up to. After that, we extend all the corrected viable up to backward to in kernel up 1 by 1 round. Here is a brief summary of results. As can be seen in the table, the T3 in the previous works is set to be 36 and 45 respectively, and in our work, the T3 is set to be 53. For the KECCAK-f, we only covered orbitals up to 6, since cases of 7 orbitals have too many candidate structures and the time complexity increases vigorously. That's all. Thanks for your attention.